Hello my dear friends, welcome to BYJU'S exam prep. In this video, we will be having an ultimate crash course which will be talking about how to understand the convection topic in 15 minutes, and this video will be helping you to solve any question from any competitive examination, that could be GATE, ESE, PSU, any exam. Just watch this video, your convection topic will be completely revised. So let us quickly start off this session. I hope so you have connected with me on my Telegram channel, and I hope so this is my mail ID. And if you see, Mechanical by Suraj sir is the Telegram channel where you will be getting the PDF of this video also, right? Chalo. So if I quickly start with the session, if I talk about convection, convection is basically the mode of heat transfer in which the heat is lost from surface to the surrounding in a very simplest way possible. So if I say example perspective, convection, what we have to do is we have to use Newton's law of convection, that is Q is equal to H into A into delta T. Normally area is already been given, temperature difference will be calculated. Only problem is how to calculate this convective heat transfer coefficient. So to calculate this convective heat transfer coefficient, we need to have the concept of Nusselt number, that is H into HLC by K. Right. So entire convection segment is revolving around how to calculate the value of H, because if you calculate the value of H, ultimately you'll be getting the value of the heat transfer. Now, if I say convection, it is broadly classified under two categories: your forced convection and free convection. Forced convection and free convection. And if I talk about the further classification, forced convection is further classified under two subcategories, that is your flow over flat plates, and your flow through pipe, right? Okay, so we'll be discussing each and every case in under 15 minutes so that we can have a complete knowledge. So let us talk about the first segment, that is flow over flat plates. Now, if I talk about flow over flat plates, how to identify the type of flow? For that, Reynolds number is being defined. So I can say if the Reynolds number is less than or equal to 5 into 10 to the power 5, then your type of flow is the laminar flow, right? And if you are having the Reynolds number greater than 10 to the power 7, then we are saying that is a turbulent flow, right? Okay, so let us start with the laminar flow. If the flow is laminar under flow over flat plates, if the flow is laminar, then ultimate aim is to get the value of small h, that is convective heat transfer coefficient. To calculate the value of h, you need to calculate what? Nusselt number, right? So I can say for laminar flow for flow over flat plates, this is a very simple formulation. The local Nusselt number is equal to 0.332 Rex 1 by 2 Prandtl to the power 1 by 3, right? Okay, but this is a local Nusselt number. From local Nusselt number, we'll be able to calculate the local convective heat transfer coefficient. And if I say flow over flat plates, we are actually calculating what is the heat loss from the entire plate to the surrounding, because the boundary layer formation is something like this, right? So in order to calculate the average heat transfer coefficient or average Nusselt number, it's a simple formulation that Nusselt number or average Nusselt number, that is Nu bar, is equal to 0.664 Rel 1 by 2 Prandtl to the power 1 by 3, and the local convective heat transfer coefficient, that is Hx, or average convective heat transfer coefficient, that is H bar, is equal to 2 times of Hx equal to L. That means I can say, if you want to calculate the average convective heat transfer coefficient for a flow over flat plates, H bar is equal to 2 times the local convective heat transfer coefficient at the trailing edge. Okay, this is your x equal to L, that is your trailing edge, and this is your leading edge, that is x equal to 0. Right? All right, fine. So this is about the flow over flat plates for laminar flow. Okay, so if I talk about for turbulent flow, same thing I'm discussing. Flow over flat plates, this is the segment. Under this laminar flow we have studied. Now we will be talking about the turbulent flow. Under turbulent flow, we can say the Reynolds number is greater than 10 to the power 7. Right? If this condition is satisfied, that means the flow is a turbulent flow. So whenever we are having a turbulent flow, then we are using the average Nusselt number is equal to 0.031 Reynolds to the power 0.8 Prandtl to the power 1 by 3. right? And it is being observed that the average convective heat transfer coefficient is 1.25, the local convective heat transfer coefficient at the trailing edge, 1.25 times the H at x equal to L. Okay, so this is the complete discussion of what will happen if I'm talking about the flow over flat plates under the forced convection. Forced convection means velocity is evident. Velocity is evident, right? Under free convection, velocity is not evident. That means the velocity is not present. It is present, but it is not having a larger magnitude. Okay, it is not evident. Right? Okay, now let us talk about flow through pipe. Now let us talk about the second segment, that is flow through pipe. Right? If I talk about flow through pipe, the range of Reynolds number is quite different. If I can say that if Reynolds number is less than equal to 2300, then your type of flow is laminar flow. And if your Reynolds number is greater than 4000, then your type of flow is turbulent flow. Turbulent flow, right? So under flow through pipe, flow through pipe or flow through an internal surface, because normally we can give a synonym to flow through pipe as internal flow, right? We can call it as internal flow also. And flow over flat plates can also be classified as the external flow, as external flow. And you can save this PDF as a quick short notes for having a quick revision for the topic of convection. Now let us talk about for the flow through pipe, the laminar flow. Let us talk about the laminar flow analysis for internal flow, that is flow through pipe. Right, Reynolds number is less than equal to 2300. So under this laminar flow, there are two subdivisions or two sub cases that we have to understand, that is constant heat flux condition, and second is constant wall temperature. This is under the laminar flow for flow through pipe. Constant heat flux we can obtain when a duct or a pipe is surrounded by an electric coil, right? And current is passing through that electric coil. That is the condition when you are fulfilling this condition, that the circumference of the pipe is being covered with a coil which through which current is being flowing. That is a condition for constant heat flux, and it is being observed that when we are having this condition where constant heat flux is obtained, then the Nusselt number is exactly equal to 4.36. Because if Nusselt number is equal to 4.36, can we calculate the value of H? Okay, and here the LC will be equal to the diameter of the pipe. If you are having a circular pipe, we'll be having the diameter. If you are having a non-circular pipe, then we'll be using a simple formulation of the characteristic length. Okay, fine, that is 2 into AB upon A plus B. A and B are the dimensions of the rectangle. Right, that is a characteristic length. Normally we will be coming across a circular duct. If you're not having a circular duct, even if you're having a non-circular duct, that is a square or a rectangle, then we can use a simple formulation of characteristic length is equal to 2AB upon A plus B. Right, okay. Now for constant wall temperature, how we can obtain this? To obtain the constant wall temperature condition, the pipe should be covered with a condensing steam. Condensing steam. Because we know that whenever I'm talking about steam, there's a latent heat, and latent heat we are talking about, there is no change in temperature. So we are maintaining the constant wall temperature, that is TW. Okay, fine. Here the wall temperature will be increasing, and when this condition is being obtained, there the Nusselt number is equal to 3.66. Right, so if Nusselt number, if in the question, what kind of question will be getting, they'll be saying that there's a constant heat flux condition for a flow through pipe, or for the fluid is flowing inside a pipe. So there you got the value of Nusselt number, that is 4.36. Place this value in this equation, HD by K, right? From there you'll be getting the value of H, and once H is calculated, you can use Q is equal to H into A into delta T, and you can calculate the convective heat transfer through the pipe or from the surface to the surrounding. Okay, fine. Now let us talk about the turbulent flow for a flow through pipe. Let us talk about the turbulent flow under flow through pipe. So here we'll be using the Dittus-Boyster's equation, that is your average Nusselt number is equal to 0.023 Re to the power 1 by 2, that is L, Prandtl to the power N. Prandtl to the power n, right? And where n is equal to 0.4 for cooling of fluid, right? And n is equal to 0.3 for the heating of fluid. Right? So this completes your complete analysis of the forced convection, right? So we have studied that under forced convection, you have studied the flow through pipes also, and a flow over flat plates also, and flow through pipe. Now let us talk about the free convection. Before going to the free convection, let me have a quick temperature variation that we are having. If you're having constant heat flux condition, I hope so you are able to see this constant heat flux condition. Under constant heat flux, we are having this your bulk temperature, and this is the surface temperature. That is the wall temperature, right? And whenever I'm talking constant heat flux, the temperature difference will always be maintained. That is the reason we're having a parallel line. Initially, we're having a slight curve. The reason for the slight curve is the starting region is the entrance region where the boundary layer is not being fully developed. And all the analysis that we are doing is for the fully developed flow. So beyond that, we're having the fully developed flow. Right? So that is the reason we never ever do the analysis for the entrance region. We always try to analyze in the fully developed flow region, and this temperature difference will be maintained. And because V is equal to, we know that Q is equal to H into delta, the heat flux is equal to H into delta T. H is constant, delta T must be constant, then only we'll be having the constant heat flux condition. Over the second condition, we are having the wall temperature is constant. So can we say the temperature difference will be gradually decreasing because delta T is equal to your TW minus TB, right? We are having constant wall temperature. The temperature of the wall will be stagnant, and the bulk mean temperature of the fluid will be gradually increasing. That means your delta T will be gradually decreasing. Okay. Fine, delta T will be gradually decreasing. That means your Q will be gradually decreasing. Okay, because H is always constant. H is not going to change because Nusselt number is equal to 3.66 for constant heat flux, and Nusselt number is equal to 4.36 for a constant heat flux condition. This is the entire discussion of the forced convection, that too flow through pipe. Now let us talk about the free convection. If I talk about the free convection, the velocity is not evident. Under this, there's a simple formulation because there is no Reynolds number because velocity is not present. There's a Grashof number, right? And whenever we are dealing with Grashof number, we are talking about a very interesting number. We call it as Rayleigh number. Rayleigh number, right? That is Ra. So if Rayleigh number is less than equal to 10 to the power 9, then that will be giving you the concept of laminar flow. And if the Rayleigh number is greater than 10 to the power 9, that will be giving you the concept of turbulent flow. In the free convection, there is no concept of flow through flow or flat plates or flow through pipe because all the surface convection heat transfer is always moving from bottom to top. Okay, even if you are having a pipe, this will be the convection heat transfer, free convection. Even if you are having a flat plate, this will be your convection heat transfer because it is always due to the density difference. Now, what will be the formulation? For this, we are having a simple formulation that your Nusselt number is equal to C times your Grashof into Prandtl to the power m. Okay, where C is constant and m is equal to, if m is equal to 1 by 4, we are talking about laminar flow. That means if the flow is laminar, then we have to take m is equal to 1 by 4, and for 1 by 3, we are talking about the turbulent flow. You're talking about the turbulent flow, right? Fine. And we know that what is Grashof into Prandtl, that is equal to Rayleigh number. Ultimately, by using this Rayleigh number, we are able to identify what is the type of flow, and after we are deciding the type of flow, then we can have the simple formulation Nu is equal to C. C is a constant, M is, we can decide on the basis of type of flow, right? And we can say N is equal to HLC by K, right? If you're having a circular pipe, then we're having a diameter will be the LC. If you're having a flat plate, then A plus B by 2 will be the characteristic length. So this way, your entire convection topic, we are able to understand in less than 15 minutes, right? So this is it from my side. I hope you enjoyed, and do share this video and save this video for future reference so that you can complete the convection revision in a very small time period. And I'll be sharing the PDF of this video in the Telegram channel, which I've already shown you, so that you are not missing a single chance to do the revision. Thank you guys. Bye bye. Take care. Stay safe and enjoy your preparation with BYJU'S exam prep. Thank you.